All right, good morning, everybody. How's everybody doing? Say hi to me in the chat if you are with me, and let's go ahead and get started. Today we are going to have to end a little bit early just because I do have a test next period, so let's get started here. So we are going to be using this table extensively this lesson, and for the quiz, we're going to have a quiz on Wednesday. Basically, there's not going to be So you guys have some new homework is going to be due Wednesday, and then I'm going to go over this stuff, and then you're going to have a quiz on Friday. Okay? So let's do this. All right. We have, last time we went through that example, and we want to do the same thing for a couple other examples here. All right? So we have zinc and copper 1 chloride, and let's see. Let me just get everything here. All right. Okay. So we got 3 people here. Who are you? Say hi to me. It's probably like Jonathan and Leo and I don't know who else. All right. So we got zinc metal and added to a solution of copper 1 chloride. Yep, Jonathan as always. All right, everybody else. And Max is here. All right. Hi, Max. And so what's going to happen? So same thing as before. We've got the zinc, and this one may have been, I just realized, a little bit trickier because zinc is a transition metal, so you might be wondering, okay, what charge does it form? And if you're ever wondering that, you're saying, okay, what does zinc turn into? So zinc metal, and you're wondering what it turns into, you can go back and look at the table here and find zinc on here. So we just look, okay, zinc's way down here, right? So zinc, and you have zinc 2+. So we know that zinc goes to a 2+. And you don't find zinc anywhere else. Some of these things like copper have multiple different possibilities, but zinc is always going to be either just, zinc metal or zinc 2+. Okay, so there's only one on the table, so that'll help you out if you're not sure what charge that forms. All right, so zinc metal, Zn, is added to a solution. So this is a solid added to a solution of copper 1 chloride. Well, we know chloride is always Cl minus. Copper 1 is Cu plus 1. And so it's an aqueous solution, so it's simply CuCl Aq. All right. Oh, Henry's on. All right, how's it going, Henry? And Eliana. Eliana, I heard you guys are moving. When are you guys moving out? All right. Anyway, so this is going to be aqueous solution, and it's going to turn into what? All right, so this is single replacement. So zinc's going to come in, replace the chloride, and you're going to end up with, zinc's going to come in, it's going to replace the copper, and it's going to turn into zinc chloride. And so the question might be, okay, ZnCl what? How many Cl's are going to be with zinc? And of course we said, well, zinc is always going to turn into Zn2+ based on the table. So really, really important. If you're not sure, okay, what the formula of this should be, right? You look over here, find zinc, and say, okay, zinc is going to be 2+. So that's why this is ZnCl2. And this, of course, is going to be Aq, and then plus Cu over here. S. And it doesn't matter which order you put these, okay? It really doesn't matter. You could have the Cu first, like we did up here. We had the Ag first and then the magnesium nitrate. So it doesn't really matter what order you put these in. That's fine. So that's the first equation. All right, like in 2 months. Okay, all right. Well, have a safe trip and have a fun time down there. All right, so next, looking at this equation, we've got zinc and copper 1 chloride goes to zinc chloride or zinc 2 chloride and copper metal. This is not balanced. Let's go ahead and balance it. If we have 2 chlorines here, 1 chlorine here, we know that we need to put a 2 in front of there. If we have 2 coppers here, we need to put a 2 in front of here. 1 zinc, 2 chlorines, 2 chlorines, 2 coppers, everything's balanced. All right. So that is the first part And let me make sure I'm going through, I need to make sure I'm answering all the questions because there's a lot of questions involved in each of these. Let's do the reaction first and then answer questions about the reaction. So first is to do the full ionic equation. So all we do is we split up these things. So this is going to be, and you need to give yourself a little bit more room when doing this. So this is going to be ZnS plus 2Cu plus 2Cl minus, all right? And you can write the AQ on here, AQ, all right? And that's going to make Zn2 plus AQ, and we have 2 chlorides plus 2Cl minus AQ, and we have 2Cu S. All of our S's didn't change at all, but the aqueous things split up into their ions, right? Copper 1 ions, we have 2 copper 1 ions, and then we have 2 chlorides, we have zinc ions, and we have your 2 chloride ions. So we notice what's the same on both sides? Well, the zinc is different. The zinc changed, right? Here it's solid, here it's 2 plus aqueous. Right, so the zinc changed, so that's not the same. We have copper plus 1, and we have copper solid, so that's not the same. So what's different is this ion right here, the thing that was not oxidized or reduced. That thing is exactly the same on both sides, so we're going to call that thing right here, this is our spectator ion. Okay, spectator ions. They're the same on both sides. So what you do is for your net ionic equation, we just remove those. Then that's it. So your net ionic equation is going to look like this. It's going to be Zn plus 2 Cu plus AQ goes to make Zn2 plus 2 Cu S. So this is your net ionic equation, and we got to make sure, maybe I should label this, right? This is going to be your full ionic equation, and this is your net ionic equation. All right, sorry, this is a little bit small, just fitting that in. So this is your net ionic equation, this is your full ionic equation. Now, we also want to split this up into the half reactions, and we want to identify, okay, what's oxidized, what's reduced, and what is the voltage of all this. So let's do that now. So the half reactions are going to be just zinc to Zn2 plus, and your copper plus to copper 0. So those are your half reactions. It doesn't really matter which one you do first, because zinc is first. I'll do that one first. So there's going to be Zns goes to Zn2 plus 2E minus. And we notice here that zinc is losing 2 electrons, right? And make sure your charges are balanced, because sometimes people forget that electrons are negative. And so make sure your charges here are balanced. We have 2 minus, we have 2 plus, come together to be 0, and this is a 0 charge here, right? And if there's no charge up here, which there isn't for any element, that means this is 0 charge, okay? So 2 positive plus 2 negative is 0, which is exactly what it should be, all right? And you can leave this as 2, you can make this copper 2 copper plus, or you really don't need the 2 there. I don't care whether you remove it or not. That's entirely up to you. But I'm going to do what we typically do in chemistry, is we take the 2 out because it's not necessary when you do the half reaction. And that's going to look like this. So Cu plus AQ plus E minus goes to make CuS. So this is the other half reaction. Your copper is going to get an electron and is going to go to copper 0. So we have names for each of these, right? This one, when the zinc loses an electron, we call that losing electrons is oxidation. That's your oxidation half. And this here, copper is gaining an electron. Gaining electrons is reduction, right? So Leo says Gur. So this is your reduction half, all right? Now, in the actual reaction, you need two of these. So you need two, this reduction reaction happens 2 times for every one of these, simply because you have only 1 electron here and 2 electrons here, and the electron transfer obviously must be balanced, okay? So copper loses 1 electron, copper gains 1 electron, and zinc loses 2 electrons, and so copper is going to, this gaining of an electron is going to happen twice for every 1 time the zinc loses 2 electrons. Now, let's see, what else do we need to mention here? We need to calculate the voltage, and we do that by looking at zinc and copper on here. And so let's start off with zinc, because we started with zinc before. So we have zinc plus 2 electrons makes zinc solid. And that is exactly the opposite of what's happening, right? So we have here, let's see if you guys can see that. Okay, so we have zinc solid is going to zinc 2 plus, right? And so, all right, morning, O'Brien. So zinc solid is going to zinc 2 plus, which is the opposite of what's right here. This is zinc 2 plus going to zinc solid. So we need to reverse that. If we flip over this equation, that means that this voltage is also flipped. So it should be 0.76, a positive 0.76 volts for that half reaction. And then we have copper. Now copper is a little confusing because we have it shows up in a bunch of these things, but we have copper plus 1 getting an electron and going to copper metal. So we got to find that one. So we have copper plus 1 getting electron going to copper metal. And that's right? So these two involve copper 2 plus, which we do not have. So we're going to find the one with copper 1, which gains an electron and goes to copper metal. That's going to be 0.52 volts. Notice it's exactly the same as what we have here, and so we don't flip anything. So that's going to be positive 0.52 volts. Yes, I know that this reaction needs to happen twice for every one of these, but we do not change the voltage. The voltage is not doubled, it's just 0.52 volts, unchanged, okay? That is the voltage, 0.52 volts. All right, so our total voltage for the reaction, so our total voltage, and I'm not going to put any specific symbols on here, is we just add those two together, all right? Excuse me. So that's going to be 1.28 volts, all right? So 0.76 plus 0.52 should give us 1.28 volts, and that's the voltage. All right, so let's see, is there any other question that I didn't, oh, okay, so I didn't answer, what would you expect to observe? Yeah, Jonathan, you had a question? Just ask. So let me go back and say, okay, what would you expect to observe? I don't think we need to write this for every single problem, but you would expect to see this copper metal that's forming on the zinc metal. Okay, shouldn't the zinc be negative 0.76? No, it shouldn't. And why not? Because it's really important. When we flip the reaction, okay, so this is zinc being reduced to go to zinc metal, but in our actual thing that we're performing, zinc is not reduced, zinc is oxidized. So if you flip the reaction, the voltage goes negative of what it is over here, and so negative of a negative is a positive, right? So this is negative 0.76, so the zinc is going to be a positive 0.76 because you flip the reaction, and that's important. So the only change you ever do to the voltage over here is to flip negatives and positives if you flip the reaction, okay? But even though we have 2 of these, we need 2 coppers to make, 2 copper metals, this voltage does not change, right? You don't multiply this by 2. So this is the correct. So it is 0.76 and it is 0.5, and your total voltage is 1.28. Okay? So that's, Jonathan, you get that? So make sure that you flip that voltage if you flip the reaction. All right, so that is that. Let me see, is there anything else I didn't answer? Write out the balance equation. And this is single replacement. I don't think we need to answer that for every single one, okay? So this is single replacement. It's a redox reaction. You're expecting to see your solid copper metal forming on top of the zinc, kind of like a powder forming. Sometimes you'll get a crystalline forming, or sometimes you get a layer, just a solid layer forming. And that's pretty much it. So I think that this is sufficient. All right, any questions about this one? About number 4? Or did I forget to answer anything? I think that's everything. Okay. Let's jump on to the next one then. And if you guys come up with questions, just ask me later, and we'll go back to this one. That's fine. The next one is aluminum and nickel 2 nitrate. And you'll find both of those on the table, all right? But we can figure it out without the table so far. So let's just start it looking at it, the reaction as a whole. Okay, so aluminum metal, it's going to be Al, just a solid, and it's added to a solution of nickel 2 nitrate. Well, we know that nickel 2 is nickel 2 plus, and nitrate's NO3 minus, so 2 plus and 1 minus. So this is going to be a solution of NiNO3 2AQ, right? That's the solution. So aluminum is added to this, and we know this is going to be a single replacement, and I told you all these reactions happen. So what happens is the aluminum is going to replace that, and you're going to end up with the, let's do it this way, aluminum nitrate. And the question is, well, what's the number here, right? Well, you can look at the table if you want and find aluminum there, but in this case you don't need to, because we know aluminum is always going to be what? +1 for the first column, +2, +3 for aluminum. So aluminum's always going to be +3 when it's an ionic compound. So we already know the aluminum nitrate has a formula of AlNO3, 3. So there has to be 3 nitrates. Plus we have a, let me see, nickel, right? So we have nickel metal being formed in this reaction. All right, we need to balance this. This is going to be a little bit more annoying because of the balancing here, but it's not so bad. I'm going to balance the nitrates first. Don't balance nitrogen and oxygen separately, just balance the nitrates. So we have 2 nitrates here, we have 3 nitrates here, so we're going to balance them by putting a 2 here and a 3 there. All right? So that's going to give us 6 nitrates. 3 times 2 is 6 nitrates. 2 times 3 is 6 nitrates. So nitrates are balanced. Now we have 2 aluminums, so we need a 2 here. And we have 3 nickels, so we need a 3 there. And everything's balanced. Okay? So let's go ahead and do the full ionic equation. And you're going to need some space for that. So this is going to be 2AlS. That doesn't change at all. It's a solid. And then we have 3 nickels, so 3 Ni, and each nickel has a 2 plus charge, AQ. And now how many nitrates do we have? We already said, right? So 3 times 2 is 6. So we have 6 NO3 minus, 6 nitrates on this side, right? And on the right side we have 2 aluminums, so 2Al3 plus, and we have 2 times 3, or 6 nitrates here, and we have 3, this doesn't change, right? It's a solid, so it doesn't change, 3 NiS. Okay, so that's our full ionic equation. Then we identify our spectator ions, and so we see, okay, aluminum going to aluminum 3 plus, that's changing. Nickel 2 plus going to nickel 0, that's changing. Nitrate going to nitrate, that's not changing. So your nitrates, and this is not a surprise to us, right? Typically, it's going to be your nitrates, your chlorides, your sulfates, your whatever, your polyatomic ion. Those things are going to be your spectator ions. Spectator. Okay. So we remove our spectator ions when we do our net ionic equation, and it's going to look like this. We just literally erase it, and that's it. So it's going to be your 2Als plus your 3Ni 2 plus going to 2Al3 plus 3Ni S. That's your net ionic equation, right? We've removed the spectator ions, the ions that aren't doing anything. Next, let's do our half reactions. And we look at, okay, we just look at one element at a time. So we have aluminum going to aluminum 3 plus. And we literally don't need to include these 2's here and these 3's here. So I'm going to go ahead and just put Al going to Al3 plus 3E minus. How do I know this is 3? Simply because if the aluminum goes to a 3 plus charge, in the process it has to lose 3 electrons. Another way to look at it is 3 plus 3 minus is 0. Okay? So that's your half reaction for aluminum, and then the half reaction for nickel. And again, if you want to put the 2 here and the 2 here, that's fine. This becomes 6. All right, but I'm going to remove those in general. So we just write the half reaction for aluminum here. All right, and then we have nickel, which is Ni2 plus, and it needs to, if it's 2 plus, it's going to gain 2 electrons, right? If it's 2 positive charge here, in order to get to 0, it needs to gain -2. Okay, so plus 2 electrons, and it's going to go to Ni. S. All right, that's balanced, that's balanced. Now, we need to identify which one's oxidation, which one's reduction. And we notice, okay, the aluminum is the one that's losing electrons. Losing electrons is oxidation, so this is oxidation. That's the oxidation half. And nickel is gaining electrons, is getting 2 electrons, and so it is being reduced. Reduction is gaining electrons. Gaining is reduction. So this is reduction. All right. So once you have that, then we can look on the table and find, well, what is the different charges of all, or what are the different voltages of these things? Let's start with aluminum, and you're going to always need to flip one of these. So keep that in mind. It's not like, oh, am I going to flip one of them? No, you always flip, because these are all reduction potentials. So the oxidation is always going to be the negative of whatever's on here. So we find aluminum. All right, aluminum's way down here. It's close to magnesium and zinc, so it's in between zinc and magnesium. So aluminum gaining 3 electrons, going to aluminum metal, is -1.66 volts. Negative means it doesn't want to happen. All right. So aluminum doesn't want to be reduced. But guess what? We're not reducing it. We're actually oxidizing it. So this here is the opposite of what's in the table. If it's the opposite, if it's the flipped reaction, we need to make sure we get the negative of this. And so the negative of negative is a positive. So that should be positive 1.66 volts. Let's write that down here. So this is going to be positive 1.66 volts. All right, nickel. Where's nickel? Nickel's right here. We have nickel 2 plus, and we're going to gain 2 electrons, and we're going to get here, let's see, gain 2 electrons, and we're going to get that. And so is that the same? Yes, look, that's the same. So nickel plus 2 electrons goes to nickel 0. That's going to be exactly the same. So that should be a negative 0.25 volts. Do we turn this negative into a positive? The The answer is no. It's going to remain as negative 0.25 volts because we didn't flip the reaction. So it's still negative 0.25 volts. Okay? We don't always flip negatives. We only flip it if the reaction itself is flipped. But in this case, we are reducing nickel, so it should be negative 0.25 volts. Okay? So what you do is you do 1.55 plus a negative 0.25 to get your final answer. Right? And so your total for your total reaction is going to be what? 1.41 volts. It's positive, so the reaction does happen. All right, guys, any questions? Now, the last one is a little tricky, but I talked about it a little bit before. And unfortunately, like I said, I'm giving a test next period, so I need to end early. So what I'm going to do is I'm actually going to talk about the new stuff, and I'm going to skip this. I will go over this tomorrow in class, okay? But let me just give you a heads up. If you got, were there any, tricky points? Just a heads up on. Actually, you know what? I'm going to do let me do the reaction. I'm going to show you guys the reaction first, and then I'll do the rest tomorrow, because some of you guys may have been stuck on the reaction. Okay, so I'm going to do the reaction and then I'll go on to the new stuff. So solid potassium is added to water, and you might be wondering, what in the world does water do? So we come over here, we find the point in time where water is gaining electrons, and we know that water is gaining electrons. How do we know that? Because potassium must be losing electrons in this, right? So if it's starting out as potassium, potassium must be oxidized, which means water must be reduced. So we find where water is a reactant, and there's only one place where water is a reactant. So it means water turns into H2 and OH minus. So it's going to form H2, which is a gas, hydrogen gas. So here water is a liquid, and it's formed hydroxide, but the hydroxide's not going to be by itself. It's going to form KOH, so potassium hydroxide, right? Because as potassium is oxidized, it's going to turn into potassium +1 ions, and they're going to be with hydroxide, okay? So this is a Q, this is a gas, and this is, let me see here. All right, so this is not balanced, I don't think. Right, so we have potassium hydroxide. So what we're going to need to do in this case is we're going to need to balance this. So I'm going to put a 2 here. So that's going to get me, because I had 3 oxygens. So what I want to do is I'm going to make 4 oxygen, or sorry, before this I had 3 hydrogens. So 2 hydrogens and 1 hydrogen. I want to balance the hydrogen. So I'm going to put a 2 here. That's going to get me 4 hydrogens on this side. And then a 2 here is going to be 4 hydrogens. And so that's going to be 2 oxygens and 2 oxygens. And then we need to also balance the potassium. So a 2 right here. All right. So that's your reaction. And it's all balanced, right? 2 potassiums. We have 4 hydrogens and 4 hydrogens, and we have 2 oxygens, 2 oxygens. So that's all balanced. I will let you guys work on that. If you had any questions, you can go ahead and, use this reaction, and we'll finish this up tomorrow and talk about how that was going to work out. But I do want to start the new stuff because I do want to leave here in, like 5 minutes or so, because I got to prepare for a test. So the new stuff is going to be using the same kind of stuff. And I think I put this already up on Google Classroom. All right. And we're going to be kind of just doing the same kind of redox reactions and now turning them into voltaic cells. And so they're a little bit different in the setup. So if I were to do, let's say, so what do I have here? Zinc and copper 2. Okay. So if I were to do one of these reactions, it's basically I would have some sort of beaker, right? And I would have, let's say copper 2+ ions in the solution, and maybe this is copper nitrate. So there's NO3 minus, NO3 minus in the solution. This is aqueous, and what I would do to do the standard reaction is I would just stick, let's say, a chunk of zinc in that, and then boom, the reaction would happen, okay? And so I could just like drop the zinc in there or something like that, and the reaction would happen. So this is what we did in the first assignment. So 11.1 is all just doing this. Put a chunk of one metal into a solution of another. That's not very useful unless you just want to do the reaction. What we're going to do now is we can take these voltages, we can use those voltages to produce electricity. We can harness those electrons, right? But if those electrons are immediately hopping, let's say going from the zinc to the copper, then we can't get them. So the way that we can separate these out is kind of interesting, okay? So instead of having this all in one beaker, we're going to separate the reactions into two beakers. And this is the way it's going to look. Let's say instead of doing it the way we did before, we're going to do this now. And let's just forget about our spectator ions. We're just, don't need to worry about them. They can be whatever, nitrates, chlorides, whatever. So we're going to have, in one beaker, we're going to have zinc ions floating around, so plenty of zinc ions, and we're going to have a chunk of zinc metal. So this is solid zinc metal. This is a beaker. This is solid zinc metal, okay? And then we're going to have another beaker, which is going to be copper ions in solution, and we're going to have copper metal here, okay? Solution, solution, okay. And so what we're going to do is we're going to separate these two beakers, and so that oxidation occurs in one of them and reduction occurs in the other one, and then we link together them through a wire, all right? And we can use the flow of electrons to, let's say, power something. Let's say we can connect that to a light bulb or something like that, and you can use that to generate light or something else. So we're going to connect the wire here, connect the wire here, wire. All right. Now it turns out that this is not enough to actually work. If you were to set this up just like I've drawn it, nothing would happen. It would be, it'd look neat. You've got this cool setup, but the light would not light. And the reason for that is that after electrons were to move through this wire, you would have a buildup of charge and everything would stop. So in order for this to work properly, you need something else that's known as a salt bridge. And we're going to connect both of these through a salt bridge. Now let me make this really clear. The salt bridge does not carry electrons. Electrons do not go across a salt bridge. Instead, the salt bridge is just composed of essentially salt, ions like sodium chloride or some other ionic compound in the salt bridge itself, and those ions are going to go into these solutions or suck up ions from the solutions so that we have a balance of charge. All right? We're going to explain this in a little bit more detail tomorrow to make sure you guys understand why we need the salt bridge. All right, but let's analyze this a little bit better. Once you have this set up, you can have a voltage and the electricity is going to flow no problem, okay? So this is known as a voltaic cell or a galvanic cell, which is the basics of how a battery works. Now, batteries typically are not wet cells like this. This is wet in that it actually has water in it, right? Batteries are typically dry cells, but the mechanics are more or less the same in this as your battery. So let's see what's actually going on here. In one side, we're going to have oxidation. In the other side, we're going to have reduction. And how do you determine which side is which? Well, the one that wants to be oxidized will be, and the one that wants to be reduced will be. The one that wants to be oxidized more will be, and the one that wants to be reduced more will be. So let's suppose this is our setup, and we want to analyze it. All right, and you're going to be asking, well, which side is oxidation, which side is reduction? So what you need to do is you need to look up a zinc and copper. All right, you find this is, so right here, let's even mark them right now. All right, we have zinc, which is, where is it again? All right, right here. This is our zinc. All right, and we have copper 2, and that's going to be this one right here. And we know it's this one because we know we have copper 2 ions and we have copper metal. Okay, so don't worry about any of the other things. Okay, so these are the 2 ones. All right, now this is important. How do you know which one is happening, is going to be the reduction, which one's going to be the oxidation? For a voltaic cell, the one that is lower down is going to be oxidation. Lower is oxidation. The one that is higher is reduction. Okay, very important. The higher one will always be reduction, higher on this table. The higher up it is, the more likely it will be reduction. The lower it is, the more likely it will be oxidation. So those are relative terms, right? So we could, for example, we could mix zinc with, let's say, aluminum, and all of a sudden zinc is higher in that case. So zinc in that case would be reduction, and the aluminum would be the oxidation side. Okay? So these are relative terms. The higher one is going to be the reduction. The lower one is going to be the oxidation. All right? So it means if the one that's oxidation, it means the flipped reaction is going to occur. So we can go ahead and do everything that we've already done, everything that we know how to do. Okay? So we find once you know which one's reduction, which one's the oxidation, you go ahead and label it right away. So because zinc is oxidation, copper is reduction. So we go over here, so we say zinc is the oxidation half, and the copper is the reduction half. Okay, that's what's happening in both sides. So what reaction is that? Well, for the oxidation, that means that zinc is going from Zn is going to Zn 2 plus 2 electrons. The reduction, copper is going from Cu 2 plus 2 electrons is going to copper metal. Okay, so that's what's happening in each of these. Notice that this one's flipped. Let's go ahead and get the voltage for each of these down here. And so let's write it this way. So your voltage for the reduction half of this is going to be what? So copper is going to be, the reduction is unchanged. It's exactly like this reaction. So it's going to be 0.34 volts. Positive 0.34 volts. The oxidation is zinc. The oxidation is the reaction getting flipped. So we see this is Zn2 plus 2 electrons to make Zn, but here we have Zn to make Zn2 plus 2 electrons. So this got flipped, which means this is not negative 0.76, but positive 0.76. So this is the oxidation potential for this is positive 0.76, which means already we can tell the total voltage of this cell. How many volts would this battery produce? It's going to be 0.76 plus 0.34. So the voltage, the potential of our total cell is going to be what? That's going to be a 1.1 volts, right? That's going to be my total voltage. Now we're not done quite yet. Let me just do a couple things real quick, and that is mention what is going on here, okay? So we have a couple terms. Wherever the oxidation occurs, we call that the anode. So this zinc is our anode, all right? Wherever the reduction occurs, we call that the cathode, okay? So the electrode where the reduction occurs is the cathode. The electrode where the oxidation occurs is the anode. And there's a little saying that you can help you out. That's an ox red cat. You can imagine yourself a red. No, you can imagine yourself a red cat. Let me see. Let me do that. Oh, that's terrible. An ox red cat. Okay? So if you imagine yourself an ox and a red cat, you'll remember that the anode is where the oxidation occurs, the cathode is where the reduction occurs. Those are just terms, and that's all. All right? But, you know, anyway. Last of all, let's talk about where the electrons go. What's the direction of flow of electrons? Because electricity is the flow of electrons. Those electrons are what does work and enables this to happen. And so let's just talk about that real quick. So the electrons are going to flow what? Well, let's think about it. Which is losing electrons? The zinc here is losing electrons. And so when it loses electrons, those electrons are always going to be flowing away from the zinc electrode, right? So the electrons are all going to be going this direction. And what's happening over here? The copper is gaining electrons. It's going to be coming over here, all right? All right, one last thing is one of these electrodes is going to be gaining mass. The other electrode is going to be losing mass. What do I mean by that? When oxidation occurs, when this zinc is oxidized, what happens? The zinc metal turns into zinc ions. And when the zinc metal turns into zinc ions, this electrode is losing mass. It's losing zinc, literally it's losing zinc atoms because they're going into the solution. So this side is, this electrode is losing mass. But this copper over here, you're getting copper ions that are gaining electrons, and then they're going to attach themselves to the electrode, right? They're going to attach themselves to the electrode and turn into copper metal. So this electrode is gaining mass, right? Always the cathode gains mass and the electrode loses mass. All right, so that's it. I know there's a lot of stuff here, but follow this and go through those practice problems, and we will be back here tomorrow to go through the rest of those problems. All right, I'm out. See you guys.